All right, moving on to our third and final speaker of the session, Charlie Middleton from Next Level Analytics. He is currently the lead for the Advancements in T&E of Autonomous Systems team for the OSD Stat COE, Statistical Test and Analysis Techniques Center of Excellence. So he's going to talk about some work they've been doing supporting developmental test evaluation and assessment in challenges and guidance for autonomous systems testing.
Thanks. Okay, so I'm Charlie. Get this working first, hopefully. Let me get rid of this. Okay. I'll go back to the beginning. I've been working on autonomous systems T&E guidance for the last few years. I'm leading the efforts at the Stat Center of Excellence. So the Stat Center of Excellence, for those who aren't aware, is a Scientific Test and Analysis Techniques Center of Excellence. We're located at Wright Pat, but we're a joint organization that supports Army, Navy, Air Force, and even others, DHS and things like that occasionally too. This work is sponsored by DTENA, so Mr. Collins at the Developmental Test Evaluation Assessments branch up at Undersecretary of Defense's office. My background is I'm former Air Force, former fighter pilot, so I'm going to use a lot of basic language to hopefully keep everybody on board with not going too technical too quickly. In general, this talk and the guidance that we've been working on is intended for new people, right? So somebody coming in who's right out of college, or they used to be the missile tester at their unit, and now they've been told, hey, you're going to be the autonomy tester now. Oh gosh, what do I need to know? Okay, so we're going to start at a pretty basic level and build up from some very basic assumptions about what are we talking about, and then we're going to get to kind of at the end. If you're an expert in this and you already know all of like why this is important, I ask you to just hang on to the end, because we're going to get to the end some of the methods which relate to tools that are going to be useful for testing autonomous systems. So overview of the talk. Can we get rid of that thing too? Black bar. Why are autonomous systems any different from testing traditional one test techniques or new test methods? What challenges do they pose that are different or heightened from other systems? And what can we do about it, right? What are the methods and practices and best practices involved? And then all of this stuff that I'm talking about today is hopefully coming out soon. We've been working on a guidebook for over a year now, and it's going to be published hopefully soon at the distro A, so fully releasable level, where you can find a bunch more information about what I'm talking about today, as well as a bunch of references to, hey, here's another paper then, or another briefing with a deep dive into whatever particular method you're interested in. So why is this important? First of all, probably nobody in here really needs to be told this, but there's a lot of hope that autonomous system technology is going to be, a third offset, right? A great paradigm shift for our defense forces and our military, because it can potentially enable revolutionary things like lots of cost savings and quantities and less human training involved and faster execution and more survivability. But there's a lot of challenges involved with that: suitability, sustainability, adaptability, ethical use, lethality. That are sort of open questions about, well, how are autonomous systems going to do these? And in my mind, in fact, we heard yesterday Dr. Cummings talk about how companies have no incentive or very little incentive to robustly test things, because they just create liability that, oh, you already knew this was a problem. Why did you field it, right? So they don't want to know, right? So it's sort of as a guy with a statistician background a little bit, type 1, type 2 error sort of question, right? Of the developers and the producers assume it works until told otherwise, right? And I think it's up to the government or the warfighters and the users to insist that, we're going to assume it doesn't work until we prove it does, right? So that's the sort of mentality that we have involved here. A lot of the tools and methods that I'm going to talk about are applicable in industry, and I would love industry to adopt several of these practices and techniques, right? But the primary audience is the independent government test agency, or the independent government testers for all this stuff. And TSE is important in that way because it's where everything has to finally come together and work, right? All your developer ideas and operational ideas and all of the S&T involved has to finally come together when you test it for the first time as an integrated system. So that's why I think this is important and why it's good to do right. So again, for the new guy, what are we even talking about? Like, how is autonomy different from AI? Okay, so here's an example autonomous system. This is notional, but you could translate this into any domain almost of an autonomous system that the military is going to use. So here we've got an automobile that's autonomous. What does it have to do? It has a bunch of tasks to complete its goal. It has to be able to in front of it and around it. It has to maybe hear sirens or other verbal directions from police. It has to monitor its own status. It has to maintain the roadway. Avoid obstacles, avoid traffic, right, which is moving things that are coming on and off the roadway. Comply with a bunch of laws like school speed zones and, other, one-way streets, right? And then ultimately its real goal is to navigate to its destination. So as components of this system, it may have multiple types of AI involved. Some of them that we've heard about a bunch over the last few years is machine learning and computer vision processing that maybe have some training data, have some onboard cameras, road databases, that's a component of the system. Another component might be its navigation. It's doing some route optimization based on road databases, maybe some real-time traffic updates to give an optimal route to get to where it's trying to go. And then you might have a third AI that is trying to prioritize between optimizing my route to get there and then all the stuff I'm seeing that are obstacles and threats on the way, and decide control actions of, okay, do I need to turn? Do I need to hit the brakes or the gas here or make some kind of turn signal, right, or honk my horn or whatever? So you may have multiple AI components that are integrated together in an integrated autonomous system. And the autonomous system isn't just those software things, by the way. We're talking about integrated hardware and software, all the sensors involved, all the actuators and everything, right, working together in a representative environment. And how do we test all of that, right? Sounds like it's easy, right? Probably not. And again, this could translate to something other than a vehicle. You could easily see how if this is a submarine, the threats might be ocean life or enemy submarines, right? If this is an aircraft, the traffic might be air traffic and obstacles and threats might be enemy threats that it detects en route to its target area. So this kind of model, I think, is good for setting the stage of what are we talking about testing. And all the things we got to kind of think of in how we're going to test this thing. Big topic in a lot of senior leadership discussion the last couple of years has been trust and how are we going to get people to trust autonomous systems. Here's a perspective on trust that we talk about in the guidance is that trust is a complicated topic and it's a very human, personal kind of thing that it varies from person to person. But trustworthiness is a more, I won't say it is objective, but it's at least a more objective feature that can be measured in a system, right? And what is trustworthiness? Well, first of all, something isn't trustworthy if it doesn't perform well, right? So the number one job of T&E is always the same as it's going to be, which is, does the thing work? How well does it work, right? That's the first goal. Beyond that, there's a bunch of ilities, right? That it's got to have security and reliability and maintainability and all that kind of stuff. Some new things that autonomous systems might have that traditional operator, driven systems, a tank or whatever submarine with humans in it doesn't need to have in the same ways is the ability to be understood, to self-report problems that can't handle, to be controlled by humans when any of the above features of trustworthiness are violated. And test and evaluation obviously provides a crucial role in establishing the trustworthiness of a system. So not just the performance, but all the other features that go into making it trustworthy. One key issue is ability to be understood. And in my mind, at least, human system interfaces are key here. I've got sort of a three-dimensional axis on trust saying that, hey, system performance is a huge axis, which T&E is going to address. Human individual differences, probably T&E is not going to address. That needs to be addressed by commanders and picking the right people to drive this thing or be responsible for it and making sure they're trained and educated appropriately. But you've got another axis of human system interfaces that if the people touching the system don't have the information they need when they need it, right, at the appropriate level of aggregation and timeliness, then the interface isn't good, even though the system is performing well, and it's not going to be trusted or even maybe be trustworthy. And those people can be, a big difference is it's a lot more people than it used to be, right? So as a former pilot, if anybody wanted to know anything about my airplane, they just talk to the pilot. Can you hit this target or can you whatever? And the pilot knows. Well, if there is no pilot, then, the maintainer and the logistician and the engineers designing and building it and the commanders who are using it and the mission commander, right? And the combatant commander who's employing the system in a combat environment, they're all sort of interfacing directly with the system in their own ways. So all the interfaces need to be appropriate for all those roles, to provide the information to show what can and cannot the system do, and is it trustworthy. And by the way, I'm talking fast. I'll pause periodically for their brief for questions. So let me pause right now. And that was the sort of the stage setting stuff. Any questions so far? And also, I think we have until 12, because I think all the other rooms had 4 talks and we only have 3. So I'm probably going to talk long. I hope that won't bother anybody, but we have plenty of time. Questions, comments up to here. Anything online on the chat? Whoever's mine in the chat? No?
Like Lynn is just sharing links to the documents. They're online.
Okay. Awesome. Okay, so challenges. They make autonomous system testing hard. The way we've written up in our guidebook is we've got 2 overarching challenges, and then a bunch of specific challenges. I've got a slide on each of the overarching. I don't have slides on all the specific challenges today just for time. But you can see we've got a bunch of them, and each of these challenges is important to somebody. So somebody in here, probably their key job is safety, right? And they're like, wow, why are you talking about anything other than safety? Somebody else is going to say, well, no, data is the main problem, right? Or as a statistician, test designer, I think test adequacy is huge, right? That how can we show coverage of the operational space and all the factors and levels involved in, testing this. So the takeaway on all this is there's a ton of challenges. They're all really different. If you're thinking about this from a top level perspective of I'm the test manager or I'm the program manager, I got a ton of stuff to worry about, and it's all different. And it all causes different issues and problems with my system. And so we've got some guidance written on all these things of why is this hard or different for autonomy compared to a normal traditional system. I can talk to anyone if I'm going to dive into a specific one, but they're going to be in the published guidebook.
Going to go into any of those in detail?
I'm going to go through those top 2 in detail, so the overarching 2. But if there's something somebody wants to dive into. So yeah, test adequacy and coverage is huge. Why is it huge? Because all the environmental conditions and scenarios involved that an autonomous system might be involved in are astronomically large, right? There's billions or trillions of test cases. Because if you think about, what's the weather, right? What's the precipitation? What's the lighting? What's the temperature? What's the terrain? What's the roadway? What's the clutter? What's the coloration? Right? Where are the allies? Where are my allies? Where are innocent bystanders? Where are potential adversaries? What are they doing? Right? The list goes on of potential factors involved here. And so how do you identify all the factors? How do you define them in ways to define sort of the scope of your envelope, or your state space? If you're a modeler, right? You think about state spaces. If you're kind of an operator, you more think about what's my operational envelope. It's sort of the same thing. And how do you define what are we even going to test in this huge space? How do we prioritize what we're going to test in this space? How do we report what we have tested and what we haven't in this space? These are huge problems. So test adequacy is, in my mind, one of the biggest challenges. But again, to somebody else, safety or personnel or infrastructure might be their biggest. Yeah.
We have a question online from Piyush Sharma from ATEC asking about a rough timeline from when the guidebook will be released.
So it's been submitted to the public release process. I don't know how long that's going to take. On paper, it's 30 days, but it's a pretty long document. It's like 170 pages. So soon.
It's available for public comments now?
No, it's not publicly available now, but it will be soon. So probably not today, but hopefully in a week or a month. And if you want to contact me about when it's available, I have like a 200-person list already that I email updates to, every few months on what are we doing. If you'd like to be added to my list, then shoot me an email or otherwise contact me after this to get it. Any other questions so far?
Yeah, so given what you said about all the challenges for the test adequacy and coverage, which I completely agree, that's a huge challenge. What have you found to be helpful that's repeatable to use to help address those challenges?
So I've got a whole section of slides in 10, 15 more minutes here. I'm going to talk about some stuff. Come back with that question again if I don't address it to your liking.
So cybersecurity is a particular issue of interest for me.
Sure.
Is it ever handled in?
Yeah, so we've got, we label it vulnerabilities here, but really vulnerabilities, we're thinking exploitable and cyber related vulnerabilities is a large part of that, right? Some of it could be sort of the adversarial attacks, which might not be necessarily cyber. They might be otherwise, messing with the inputs to your system, but or jamming or right, other kind of, you can imagine autonomous systems are going to be way more dependent on data links probably than traditional systems have an operator, right? So there are all kinds of threat vectors. So vulnerabilities include cyber. And from a challenges perspective, you can see that, if we can make the system think it is or it's not, or think somebody is friendly when they're not, or what, because of some vulnerability in the way it's either receiving information or processing information, that's a huge challenge too. And it's more important for an autonomous system than, again, if you have a human operator there that can go, right, like, that's not the example yesterday with baby milk factory, right? It's not a baby milk factory, I see missiles sitting there, right? Yeah. Anybody else to hear? Okay. So the two overarching challenges that we talk more at length in the guidebook than the others is the first one is adapting to developmental test and evaluation as a continuum. So this is a big push from the folks at DTNA, Mr. Collins and his team. And this is not just applicable to autonomous systems, this is applicable to a ton of technologies that are, in development and testing right now. But the idea that we used to back in the day, right, do a waterfall type process where, industry does some testing when they're first developing things, and then at some point there's a DT&E, bucket, right? That DT&E happens before some milestone, and that's when DT&E is, and then you finish DT&E and then OT&E starts. The future is, and the now really is that it's a continuum. That DT&E belongs everywhere across the capability lifecycle. So early S&T type testing is highly valuable. Testing throughout, development and engineering and production, and into even after production and fielding. We've talked about, other folks talked about yesterday, of post acceptance or post fielding type of testing. So that's a big change. How often T&E occurs? Again, traditionally, DT&E might be a one-time verification event, and then, hey, we verified and validated, and we're done, right? It's probably going to be more of an iterative. So my slide didn't transfer, but there's supposed to be circles at the bottom there that you're going to repeatedly circle back to do DT&E events as product changes, especially if they're highly software enabled, because that's the way software is done. It's done in iterative and agile type of production and fielding, and so test has to adjust to that. And then the third continuum that I like to think about is what information are we getting out of tests? So again, traditionally, you have DT&E to answer specific V&V of requirements or specifications. So there's a key performance parameter, there's a key system attribute, right? These are in the requirements document that this has to have, the missile shall launch in no less than, 3 seconds or something, right? That you do it once, you have a test event, and then you check it off and you're done. DT&E as a continuum thinks about this, you can't read this, but there's a whole bunch of things that need truth data now. If you think from a digital engineering perspective, there's a bunch of S&T stuff, prototyping that needs data. There's M&S that needs data. There's live virtual constructive, and subsystem testing that need truth data. There's integrated system testing. There's system of systems and mission level, operational level sort of truth data needed. So DT&E is going to be a truth source for all of these, right? It's not a one-time thing and then we're done. We're going to need to, as a community, think about how are we adjusting to continuously provide good data at minimum cost, right? We still want to optimize it, like, so we don't want to do unnecessary testing, but to provide information for all these times and sources or customers. So the approach that the leadership wants folks to focus on is, providing data support, again, all analysis and studies, LVC, M&S, other test activities, have a sort of a campaign of learning construct across the life cycle, enable data-driven decision making, right, to inform decisions better and exploit digital ecosystems. So, exploit digital engineering and M&S and, data dashboards and all that kind of stuff. So that's one big challenge. The other big challenge, which is more specific to autonomy as opposed to sort of all systems in, the mid 21st century here, is T&E of the OODA loop. So somebody earlier mentioned the OODA loop. So OODA, for those not familiar, which is probably nobody, is observe, orient, decide, act. It's a decision model that came out of the 70s. Somebody wrote a paper on how warfighters think about and fight in combat. So in legacy systems, you've got, traditionally, I've got some requirement I got to verify. I have some test point condition, which might have what is the target or what's the threat, what kind of range is it at, and speed and altitude or depth, and what kind of control is it using, and maybe there's some electronic warfare, jamming or whatever in your test point condition. But you've got, here are the conditions for this test point, right? And you run the test point, and there's a single test point, you get some kind of response, and the response is going to be a missed distance or track time or some maneuver that comes out of it. And you have a matrix of these test points, and you go through them, and you're done, right? Autonomous systems, you have to think about, are dynamically interacting all the time with a bunch of things in the real world. And so we have to be able to test a whole cycle continuously through not seconds and minutes, but maybe hours and days of duration of what's happening in the environment with navigation, with clutter, with targets, with other agents, which could be manned or unmanned, or other environmental conditions, and observing all of that with sensors, maybe communications, or other means, and then fusing that into orientation, having models of the world and models of my own status, right, and making correct decisions based on the sensor inputs as to how I'm modeling what is happening in the world, right, in my systems brain. And then there's a decision step, right, of, okay, based on where I think everything is, and threats and options and goals I'm trying to reach, what decision I'm going to make now, or am I going to delay a decision maybe and wait for more data? And then how does it carry out that decision, act? And then, there's a continuous feedback cycle of when you act, then did it get the response that I wanted, or is there's some other new input now I need to, continuously reorient and act. So from a test perspective, this changes how we have to plan tests, how we have to instrument tests, how we have to analyze data from tests. It makes it a lot bigger, a lot more complicated. So this is the other real overarching challenge in my mind for autonomous systems that we need to tackle. And so some of the methods later are going to talk about some of those problems and issues and what we can do about it. So this you probably can't read, but what we did is we tried to put all of the challenges across the top, and then all of the 29 total methods and best practices across the left side here, right? And say which challenges are addressed in some way by any of these methods. So if your concern is data, or your concern is safety, or test adequacy, right, then you can flip to the section that cover, okay, there's like 6 things that cover data, or there's 12 things that talk about safety that are safety related in the methods and best practices. So help to kind of orient folks to sections of the best practices that they think might be applicable. With the idea being that this is an emerging technology area. We don't have all the answers, but we've tried to gather what has been useful to somebody in AFRL or in Army in Research Lab or wherever in some kind of autonomy testing over the last few years. What was the problem? How do they solve it? What are they doing? And can we write that down and help somebody not reinvent the wheel, at least get them started in the right direction with some ideas? So it's a menu of tools in your toolbox that you might want to use if you're having a problem with something, right? And we don't promise that any of these are going to guarantee success or that they're sufficient in any way or exhaustive, right? But this is a snapshot in time of here's what we know about autonomy testing so far. And here are a bunch of things that we think are good to do. And it's up to you to decide, if you're going to implement them in your program or your project. Okay, let me pause there again for a minute. Any questions on what I covered there with the challenges? Yes, ma'am.
Yeah, great information. So this is like a new space for me. I come from as a user experience researcher over in the consumer tech side. Trying to get plugged in. I think what I'm trying to understand and what I've been struggling with is there's a lot of talk about the importance of human-computer interaction, good design interfaces, trustworthiness, autonomous design, which I think, maybe I'm biased as a UX researcher, involves, bringing in the user at different points of the software development process, whether it's the military calls DT or OT. I was hoping maybe you can tell me about when does the military bring in the actual users during this kind of DT thing process?
Yeah. So yeah, absolutely. I think all of the services have recognized that, yes, you need user involvement. They each do it differently, right? So there's no one answer. The Army will bring stuff to an operational unit and, let them kind of play with it for a day. And they're just normal infantry guys or whatever who don't really have any special training on something potentially. In some cases, right? In other cases, they do it differently. The Air Force or the Navy for aircraft, you don't let the newest guy go test your brand new, multi-billion-dollar experimental airplane. They have highly trained test pilots whose whole job it is to test new technology, right? And they have operational experience and background, and got handpicked to be, hey, you're the guy that we're going to have lead the testing from a user perspective on this. So they all do it differently, and they all do it at different points in the life cycle. And sometimes it goes great, and sometimes it doesn't, right? That people get this wrong. But there's definitely widespread acceptance that, yes, absolutely, getting user feedback in some form at multiple points throughout development, and engineering, manufacturing stages and those kind of things are very important.
Oh, quick follow-up, sorry, I won't take up too much. And so do users in this space tend to trust the system by default more than, because at the consumer side, if something doesn't work for 5 seconds, they'll go to the board, right? But
I would say, again, it depends,
okay.
But so I'm a former pilot, and there's a mentality among pilots from ages and ages beyond before I was born, probably, that I can do this myself, right? That I don't need the autopilot. I'm going to hand fly it. I don't need to, right? I'm going to rely on automation and technology as little as possible because, I want to be in control. I don't want some system in control. I want to be in control. The problem comes when you get more and more tasks loaded, right? And so you become task saturated and overloaded with information, overloaded with things you got to manage. And then you need to start offloading, right? And I'm working my radar. I'm trying to find a target. I'm communicating with my women. Maybe it's a good time to have the autopilot on, right? So in my experience, users tend to not want to give up control and to automation unless they need to, or unless they're told to, right? Commanders could sometimes just dictate, this is the way we're going to do it, and there's no arguing. And it's the military, so that's what you do. But yeah, I think generally there's a distrust of things that are new or different from the way you were trained. Because you were trained to do it, the old way, right? And so I can already do this task. Why do I need some, right? There was auto ground collision avoidance was mentioned earlier today as a great success, and it is, but it took way longer to get auto GCAS put in the F-16 than it should have. I mean, there were dozens of pilots that all died in completely avoidable scenarios with a perfectly good airplane because they flew into the ground, where if we'd had the system 20 or 30 years earlier, they'd be alive today. And that is just from there's probably a lot of reasons behind it, but one of them is that there was a sense that, no, we can train and we're going to avoid this just with training and being better pilots, right? And at some point, somebody decided, thank God, right? There's technology and works really good. Why aren't we using it to save lives? And somebody decided okay, yeah, we're going to finally spend money on this. And so that was a long sidebar, but I don't know if the answer to the question, but there's not always immediate acceptance when something new comes out, a new way to do things, right? There probably wasn't immediate acceptance when we all got iPhones and they have GPS, and how to find your way to your friend's house on there. But over time, it got better, and now we all use it, and nobody uses the map anymore, right? So that's kind of the way it works usually. Any other questions?
On the slide where you're discussing the ICT and testing the OOD.
Yeah.
It seems like part of what you're saying is that if for these kind of complex systems that have many steps and possibly many components in them, if the mission outcome is not expected, you want to be able to do fault location or analysis. You want to figure out where things went wrong.
Yeah.
And so what I'm just curious about is do you think that teaming of autonomous systems, given how complex they are with many components, is actually different because they're autonomous, or it's different because they're complex? And would it be the same as if you were testing, say, like a complex cyber physical software system that didn't have autonomy, that had many components, and you wanted to therefore do this kind of like unit testing and execution testing system?
Yeah, I mean, I think they are more complex, and that is a lot of the reason why it's hard. It's harder, but I also think that fundamentally, we're asking our systems to do things that we didn't used to ask them to do, right? If I'm driving my Toyota and a kid rolls a basketball into the road in front of me and chases after it, then the Toyota doesn't have to stop. I have to press the brake pedal. I have to see it and press the brake pedal. Now we're asking the vehicle to do that, right? That is a whole new task, a whole new type of capability that cars never had, right? Of, recognize a kid and recognize it coming in the street, and recognize it in your path, and recognize you're going to kill them, right? And recognize that I can stop if I press the brake now, right? So we're asking our autonomous systems to do things that we haven't in the past. So yeah, they are more complicated, but also the capabilities are different. So that's the answer to it. Any other questions up to here, sir?
Actually, I'm going to respond to her question, and it has to do with varying levels of incredulity. In the early test and evaluation process, most of the operators that are involved are interested in, hey, I don't have to take this home. I don't have to make it work. Tell me what you want me to do with it. Eager to see that it improves. So they'll be quite candid, and they'll usually go, hey, did you tell me what I'm supposed to do with it? Did you manage my expectations? But then later on, when it gets to more operational testing, there's a little bit increasing incredulity. And then there's an education phase. Later on, when it becomes new equipment training, hey, we bought these and now you have to use them, incredulity rises a lot more. And so there's this whole dedicated training regimen to help overcome that barrier of doubt. And then we see how it is actually used and whether or not they apply it in the way that it was originally intended.
Is the training effective? To kind of break
That's a
down.
different question.
Okay.
But in terms of the training effective and managing expectation and working with that levels of doubt, yes. But then it becomes, now that they're actually using it, does it perform as they were educated as how it works, right? And so that level of education and the time, and then their level of experience with it, then that varies as to. But now we're talking about the measure of effectiveness of the actual training versus, but there is a correlation.
Okay.
And most people in the consumer world don't get that kind of, they find the instructions and they throw them away because they know how to do it, right? So we take a little bit different approach in the military sciences of you're going to receive training and your equipment.
Yeah.
There you go.
Okay.
Might also have one other tip to that, right? It's not just training on how to use the equipment, but you might hopefully decision makers are getting training on the risks, right? Because they have to take on liabilities, which consumers don't necessarily take on in the same way. I mean, they take on liabilities.
Yeah, I'm still working
Right.
or something, right?
So there is another difference where you're taking on risks, so you actually have to do training. And that's a whole discussion, like how do you train people on AI risk or autonomy risk, what they're taking on.
Yeah. I can.
Okay, so I'm gonna move on so we can get through. So this is now what I've been waiting for, which is, okay, what can we do about it, right? What are the methods of best practices? So there's a bunch. I don't have time to go through them one by one. I will deep dive into any ones you guys ask about. The three I have slides on are what we call the overarching methods, right? So end-to-end process. So this is an overarching framework for how we're gonna probably best test autonomous systems. Staff autonomous systems, so answering some of the test adequacy stuff is a big part of that and a big part of where I work. And then M&S, and how does M&S complement autonomy T&E? So those are kind of the overarching ones, and then there's 26 other ones. I've got them bucketed into sort of where they fall in the life cycle as far as like where they're most applicable. Many of them cross between life cycle phases, so you really need to kind of understand all of them from the beginning, but that's how they're arranged, at least in the slides and in the guidebook that we're writing. So end-to-end process. So and let me say also, I am not an expert in any of these, right? I'm putting together all this information so somebody who doesn't know what they're doing can use it, right? So if you want, who is the expert on this? It's not me. I had great support from folks who helped write this and helped design the graphics and things, who are experts in all this stuff. So this one came from Dave Scheit, who's a Naval Air Warfare Center guy who's been doing autonomy for 20 plus years. And this is the end-to-end process. So the idea here is that there's a ton of stuff to test. We talked about test adequacy. And how do you do it? You start with a limited objective. And the limited objective could be a small set of environmental or other scenario parameters. It could be a limited objective as far as the tasks or capabilities being tested in the system. You start with a small experiment, right? And you're going to do a large sample, low fidelity examination first. So think simulation, probably, although it doesn't have to be simulation. And that low fidelity test is going to give you a bunch of data, and you're going to analyze the results. And then you're going to say, where can we get the maximum value? Looking at the results from all this low fidelity testing on our low sample, right? Meaning few, and high fidelity, meaning more expensive, but better data, live test events, right? So, and then you're going to design a test that's fewer runs, but better, more realistic data. And you get some data out there, and then you're going to compare and say, are these consistent between the low fidelity and the high fidelity stuff? And if it is, then great. We're going to go increase the scope of testing. If they're not, you're going to go change your models and assumptions for your low fidelity stuff and rerun your low fidelity stuff and get better and iterate that process until you get consistent results. And then you're going to increase scope, saying, okay, now we're going to do more scenarios. We're going to do more speeds and ranges or target types or whatever, jamming. But you think of all the scenario conditions, right? And do iteratively bigger experiments where you simulate or you do some low fidelity thing first, and then you do some much smaller sample size, high fidelity. And you repeat this process over and over until you're happy. And what does that larger, what does that larger cycle look like then? Well, starting from mission requirements, you need to understand what are the autonomy requirements among my mission requirements. So there's a bunch of mission requirements that maybe aren't related to autonomy in your system, but the ones that are related to autonomy, you have this iterative gray box, which is basically this thing on the left, with large sample but low fidelity. So context independent testing, factually real-time simulation, formal analysis, formal verification is even one here, right? That you can have just mathematical proofs of algorithms used to verify some capabilities or some tasks, right? And then you feed that in a loop with that kind of higher fidelity stuff, which might be pilot in the loop or operator in the loop. Virtual constructive testing might be other LVC, live virtual constructive development testing, operational testing, or larger formal verifications that are sort of the, at the design level. And then you're going to get some body of evidence that's going to be multiple sources at multiple fidelities, right? And you're going to have to do some kind of evidence aggregation where you make a certification argument over top of that with some runtime assurance, meaning some kind of safety backup system, right? For making sure that you don't go out of bounds in catastrophic ways. And you're going to put all this together into some certification arguments to certify that the system, and then continuing validation, because again, software is probably going to change over time. The tactics of how it's going to use are going to be changing over time. The threats are going to change over time, right? So you need some kind of continuing validation cycle here as well. So this is sort of the overarching framework that all the other methods sort of fit into in some way. The second overarching one is scientific test analysis techniques. So STAT for autonomous systems, hypothesis-driven approach, making sure that your test strategy and test plans are all data-driven and, right-sized to optimize maximum information with minimum testing required, right? So there's a bunch of benefits from that, accurately characterizing the system, assessing both the breadth and depth of what you plan to test or are testing, so you understand risks, allowing iterative testing for continuous improvement, and how different conditions and scenarios might change performance trustworthiness. And I'm not gonna read them all, but bottom line is the use of STAT is required for DoD systems by DoD regulations. It has a bunch of benefits that go through, from early STAT activities, making sure that your requirements are comprehensively analyzed and broken down, and you identified measurable behaviors and test objectives well, generating, what are the factors and levels, inputs and output data needs involved, making sure that you account for constraints, limitations, understanding the combinatorics of all the conditions state spaces, doing good analysis on that, for comparison of models versus real data, and understanding goodness of fit and other metrics to say, how well are my models fitting my testing, and there's some best practices that go along with that that are related to autonomy, which could include things like sequential testing, Bayesian statistics, et cetera. So that's the second one. The third one is modeling a sim for autonomy T&E. So M&S is a powerful framework for analyzing, testing, and refining autonomous systems. Again, Dr. What's her name? Missy yesterday talked about how commercial companies don't want to do any live testing. They just want to do M&S only and say, we're done. It works. It's good, right? I don't think that's the right way for DoD. As I said in the lower left there, I believe M&S is a complement, not a replacement for live testing, used to its best, optimal application. But there's a bunch of benefits you can get from M&S for autonomy T&E. You can early identify issues. You can validate capabilities across a bunch of conditions that maybe you don't have the time or money or whatever to test. You can do multi-domain stuff via simulation. You can test interactions, via simulation early. You can do a bunch of cost savings by simulating a bunch of things instead of doing them live. Mitigate safety and security risks that we can simulate things that we wouldn't dare do because they're too dangerous or they're too classified to do, like out in the open air environment, right? And you can iterate more quickly in simulation. So there's a whole bunch of types of simulation. You can test cognitive models of simulations of how the thing is thinking, right? You can do system models. You need environmental models of how are we modeling the environment in my simulation. And then there's different types of simulation. Again, cognitive simulations, fast and real time, virtual constructive, meaning, maybe some don't have humans involved at all. Some simulations might have a human involved as part of the simulation, right? There's a bunch of uses of simulations, from requirements to testing to, human loop, LVC, et cetera. And then there's some good impacts. And then we've got some best practices again, related to autonomy. The big one, one of the big ones is, in my opinion, independent government-owned simulation capabilities. So that was a question earlier of, hey, isn't M&S a great answer, and why don't we have more M&S? Well, so we are developing, all the services have some kind of M&S capability that is government-owned and managed, and needs to be improved, needs to have awareness that's available, put out there, needs to be validated and standardized, right? And I'm going to talk more about the end as far as future steps on this work, for infrastructure available, kind of stuff. So let me pause there before I get into the charts on the other 26 methods real quick. Any questions on the main three that we had, sir?
One thought, could we go back a couple slides to the iterative process on the right there? That is expensive. And individual programs of records will not be able to afford that. So my suggestion is, as from an OSD or DoD perspective, we need to figure out how to attack that from an enterprise perspective such that multiple users can use this infrastructure. Your one ACAT2 element that may have an AI piece to it, in a combat systems, for example, may have an AI and another program manager's ACAT1. And those two have to be able to, from a systems of systems, interact with each other. So you can have multiple individual programs of record that all need this, that are never going to be able to afford it. And so I think the only way we actually get after this is do an enterprise approach of, something, one, to be used by all as much as possible, I just don't see this happening in the current, the way we get after acquiring systems and all that. It has to be done at a higher level, just my thought.
Sure.
And then the second thing, for operational testing, in this context of developing software and getting it out quicker, we're gonna have to pull OT left, right? And you're gonna wanna pull DT right. So what we're gonna wanna see is the actual user. In a lot of cases, it's not gonna be an 06 pilot, right? It's gonna be an E3, fire control, right? So we're gonna wanna see, and that's risk for the PM, right? Putting the less experienced user in there on a less mature system. But we've got to think about how we're gonna do that if we're gonna get faster. So two things, again, expense, how do we get after building a larger enterprise infrastructure for programs to come test? And then two, pulling the actual user to the left that may not be the one with the PhD, right? Your user's not gonna have a PhD. Your user may at best have a associate's degree in a lot of these instances. So we're gonna wanna see that actual user left, and that's risky.
Yeah.
Typically, and it's a trust game, right? Between how much does the program manager let OT far to the left, right? And then how much do we trust the developmental test infrastructure and data to be used for OT?
Yeah. Can't argue with any of that. I will say that I see this process as not a single point in time, somebody has to do all this.
Right.
That this starts in like the lab, right? In the TRL 3 or 4, right? That you start building this low fidelity stuff and the high fidelity, small use case kind of data early. And you need to hold on to it, have good data architecture, manage your data, digital engineering, all those good buzzwords to build that evidence aggregation eventually. This is one of the reasons that we need to think of that continuum of learning throughout the life cycle. So that it is tractable and not, prohibitively expensive. My other thought on this is that the beauty of AI and autonomy is that, theoretically, if I do this correctly once, like I never have to do it again. We've trained thousands of sailors, coal rigs, to have how to drive ships without hitting each other. If I can train an autonomy to do that correctly once, we never have to train anyone again, right? Flying an airplane, flying formation, hooking up with a tanker or whatever. If I can train an autonomy correctly to do this, and then it's transferable to other airframes, right? Which may or may not be, but now we've solved that problem, like for all of the future of humanity, right? So doing this correctly, in my opinion, is, it might be a massive investment, but the payoff, like down the road, is,
It's always the struggle.
Right. That's the promise.
Dividends later.
Yeah. Right, I know, yeah, in a palm cycle, sir.
Yeah, to the autonomy requirements analysis, it seems like programs seem to be looking for the future use case they want. Whereas if we are scoping these requirements in more tractable pieces for specific subtests or kind of smaller, simpler missions before we go for the bigger, more complex environments, cooperative engagements kind of thing. Have you been talking with programs or recommending processes to kind of start small and kind of iterate with what you are certifying these autonomous systems for?
Yes. Everybody I've talked to, so again, Air, Land, Sea, they all see these same problems. They all see this is massive. Where do I begin? And they all realize we got to start simple. You got to walk before you can run, all that. Everybody says the same thing, right? So we've advised, for example, the AFRL project with Skyborg a couple of years ago. We were involved with some of the simulation there, and they want to know, like, how do we manage what we only have time to simulate some, how do we manage what we do? And, so we suggested, well, you want to start with each individual maneuver and simulate that individually. And then when you're, now you want to chain together maneuvers, what's the smartest way to do pairwise chaining of maneuvers together in different orders, right? To be more efficient and cover the space, so I forget the question now, but I don't know if I answered it. I think people recognize that across all the services, this is hard, and you can't bite off the fully realistic, whatever, Taiwan Strait scenario in, your second week of testing, so. Okay, we're gonna run into lunch. So, I'm gonna have to talk faster and faster, which you guys probably won't like either. Okay, so I'm not gonna go through all these. I put them in here again, so you can reference it either later or, oh, hey, when the guidebook comes out, I want to read more about, code isolation or whatever it is. But real quick, so these are what I've categorized as ACT strategy or development strategy. So again, this is a test thing, but some of your test capability and test effectiveness goes all the way back to how did we design and build the system? And did we build it correctly to make it testable in smart and efficient ways, right? So this is talking to that. And somebody mentioned modeling earlier. That's the first thing on my list is you got to have good operational modeling of what is the concept, how this is going to work, what's the con-imp, what's the con-ops. In traditional systems, you can say, hey, here's a new gun, go figure out how to best use it, or, a tank or whatever, and they'll figure out the con-ops later because there's humans driving it. In autonomy, you got to figure all that out ahead of time, right? So this is one of the challenges. And so having storyboards and other types of good modeling for all the tasks that it's going to need to do so that they can be designed and the requirements are good and tested, right? That the testers need to understand, like, how is this going to be employed? I can't really test it right if I don't even understand what it's trying to do. That's a huge step. Small scale development, open architecture, yeah. Continuous testing, I kind of talked to earlier that test is a continuum. Both left and right of traditional DT is important for these systems. Assurance cases, I kind of talked about that a little bit. So there are established tools and ways to do assurance cases well, where you combine multiple data from multiple different sources and aggregate that to build a compelling argument for certification or safety or security or whatever your concern is. Okay, getting into test strategy. So live virtual constructive is right at the top. It's a huge one, right? That to be efficient with our resources, we have to only test live things we really need to test live. We need to do maximize virtual testing, meaning maybe humans involved, but otherwise simulated, and maximize constructive testing, meaning everything simulated, right? And maybe those are all three combined. And this has happened, right? Where there's live assets flying on the range. At the same time, there's digital assets simulated through data links on the range, and maybe a pilot in a simulator flying an adversary that's data linked to, into the scenario that you can combine all that, right? And save a lot of money and time and complication in your testing if you do it correctly and still get the data that you were looking for out of how's the system performing. Experimentation is big now, of testing, not really to validate requirements, but really to just learn, right? And how do you do that well? Use of surrogate platforms to test beds, the sandboxes, right? Surrogate platforms are huge. Form for exchange hard hit, adversarial. We had a guest speaker earlier. Post acceptance testing. I think everybody gets the idea that threats and tactics and things are going to change after fielding, and so continued testing. As things change, is going to need to continue to happen, even after acceptance. Test planning wise, there's a bunch here. AI model testing needs to be understood as part of doing your integrated system. You need to understand how was the AI tested so that I can validate that was all correct, and I could scope my live testing to cover the things the AI testing couldn't cover because it wasn't realistic enough or they couldn't get data or whatever, right? STPA, somebody mentioned as a safety and control type of best practice for managing risk from a safety perspective in some of this testing. Human autonomy teaming, there's a bunch of stuff there. I know it's a short bullet, but that's a really complicated one that we've got several pages on. Metrics for situation awareness and role clarity and communication and collaboration, that you test all of those things appropriately. Because the human teaming is really critical, even though you've sort of taken the human out, it's still obviously critical. Automatic domain randomization is one, kind of like injecting the fuzz right in your picture, or actually from a software perspective, fuzzing is actually what it's called, right? When you put in like weird bogus inputs and stuff that can be applied in an autonomy perspective by automating how you tweak parameters either in the internal settings of the system itself or of the environment and the simulation or the setup or whatever of your test event to make sure that you've got robustness, that it's not doing some single point weird solution, that you're getting relatively consistent results, even if you make small changes in the inputs. Failure path, outlier search, yep, those are good. Cognitive instrumentation, so somebody talked earlier about, we need to understand that whole OODA loop. How do we do that? Cognitive instrumentation is the idea that we need to instrument and we need to build in instrumentation to our autonomy to see the steps of that OODA loop in my test data, maybe real time or at least after the mission, right? To understand each stage of what did the system see? What did it fuse that to change its models? What decision to make off of that, right? And the cognitive instrumentation is how we do that, seeing the internal workings inside the brain of the system. And then building the data analysis tools, obviously, to handle all that data. Runtime assurance, again, the idea that, I've got an instructor pilot sitting next to me, right? That if my autonomy engine crashes in flight or in, wherever, in the water, that there's some other system that's going to keep the thing from crashing. It's going to allow a reboot. It's going to, take control, potentially bring back a safe recovery of the item. That's critical. But then, of course, that assurance system has to be tested as well. So creating a standardized runtime assurance that can be reused across multiple platforms and the test ranges and whatnot agree that, yes, we're happy with it. That's a way to save time and money over time and make things repeatable. And some of these things like runtime assurance and cognitive instrumentation probably don't need to be pulled out when you deploy it in the field, that you actually want to keep runtime assurance in when it goes to its final fielding, right? And keep cognitive instrumentation in so that as it's being operationally used, you still get data from the field, right? That you can continue to analyze across the life cycle. Okay, and then I'm almost done. Data analysis evaluation. So this is just some ideas here about, can it work better than a human, right? And how do we measure that? There's some thoughts on that for best practices. Task-based certification is one that I think is great. So in the DoD, people ask, is it accredited, right? And accreditation is this one time like, oh, it's accredited, like, don't ever say it wasn't accredited. Like it's been, it's accredited now and for all time. We're going to say it's accredited, but and really how things work is things should be accredited for a specific task or specific use, right? And then you revalidate and reaccredit things over time. So the idea here is that autonomous systems are probably going to need to be certified for tasks that it can safely do, that we've tested and proven it can do, and then over time those tasks are going to grow. Just like as a pilot, I'm initially not cleared to fly at night or cleared to fly with night vision goggles or cleared to, use the most complicated weapon. That you build up those skills over time. Autonomous systems are likely going to need to be certified in the same way, where we slowly build up the skills that the system can safely and effectively, trustworthy, right, do. And so having our test setups and our certification setups matching that sort of framework mentality, I think is a good deal. Okay, I've talked fast. This is my last one. So there's a guidebook that we wrote. Like I said, it's in the publication process now. These are the chapters. We just talked a little bit in there about policy. I didn't cover that today, but I covered most of the rest of the meat of it. There's a glossary in there too for terminology and for new folks. What are we doing next? So the current guidebook is distro A, or the Boston one to be public and releasable. So it is. What does that mean? Is that it doesn't include a lot of things testers might want, like T&E resources, tools, facilities, platforms, et cetera, because a lot of that stuff is actually CUI. So we're planning to do a expansion probably this year or next year into resources for autonomous systems, covering DoD test labs, test ranges, other test facilities. Somebody might have NIST or Python stuff or whatever, right? That are going to go into our addendum. So it could be hardware resources, could be software resources, test beds, et cetera, and then simulation environments. So AFSIM, NATS, ACTS, right? These are acronyms that stand for simulation capabilities that Army, Navy, and Air Force are building that are government-owned simulation environments. And so we want to list out how do these work, who owns them, how do you get involved, if you want to use it, right? And then we'd like to have examples of case studies. So I'll need help from you guys on this, right, who are doing this, of land, sea, air, space, swarm autonomy, what has been tested and what was learned from the test, what were lessons learned. Everybody always loves case studies. And we want to update our guidebook because this is an emerging technology area. So we want to get rid of the methods that don't work, or people say, no, that, we tried that and actually that wasn't. But if somebody has a new method or a new challenge, we want to add that as well. So that's it. I'll leave it on this one. Questions? Sorry, I went long.
break. So let's thank Charlie for the talk.